Okay. So, allora, premetto che faccio questa premessa in italiano che non sono sicuro che tutto stia funzionando correttamente, mi riferisco a chi ci segue in remoto, e non sono sicuro di accorgermi qualora mi scrivessero, quindi se per caso qualcuno che voi conoscete vi scrive, fatemelo sapere, insomma, è un po' un learning process, soprattutto per me, quindi cerchiamo di venirci incontro. Se nel frattempo chi mi segue in remoto riesce a confermarmi che va tutto bene, bene.
Sì, per ora nessun problema.
Benissimo, quindi riuscite a vedere le slide?
Aspetti, no, un secondo. No, no, le slide no. Lei la può sentire, ma non ci sono.
Ok, allora vedo di condividerle. Ok.
Ora sì.
Le vedete?
Sì.
Benissimo, molto bene.
Grazie mille.
Ok, allora I switch to English because I am supposed to speak English. And I don't mind. I hope you don't either. So, if whenever I say something you don't understand, either because of the content of what I'm saying or because of my English, just raise your hand or just let me know for the people who are remotely connected. So I apologize for the delay due to several independent reasons. So just to let you know, so as you probably know, this is the first, I don't know where to look. Well, I look at the computer, I should better look at you, at least you're, so please forgive me my being uncomfortable, a little bit uncomfortable, I will get used to that. This is the new course, new mandatory course, and I wanted to present in a few words, in a few slides, the essence, the concept of this course. So the lectures, as you might have guessed, will be always delivered through slides. Slides that I'm gonna share with you. Well, today is a kind of a one-of-a-kind lecture today because it's the first one. But normally I will invite you right now from now you to drop me your email address. I will collect all of your email addresses and we will share with you on Drive a folder in which I will put all the presentations. So everything you're going to see today and the next classes is something that you will have access to, okay? So don't get crazy to write down what you see on the screen. What you see on the screen is already available to you. Just make sure, possibly to write down what I say, which is not on the screen, whatever you want, but just to let you know. Okay, this is something I already said. The bibliographic sources are several, but for each specific topic, and you will see at the end of this class, I list the specific, and I will give additional comments of what textbook I use for some specific topic, okay? So if you want to go deeper into something, you want to understand from the very basic source, plenty of bibliographic sources will be provided. The final exam, well, it's just oral, no written exam. So this is the first piece of news which should make you happy. The second piece of news is just typical duration, 45 minutes, 1 hour. And sometimes, occasionally, I call this simple exercises, which means just to see how familiar you are with very basic estimations, calculations. I will make several examples so that you can figure out what I mean now. So as I said, this is the first time, this is the first year that such a course is delivered to all of you. So I'm sure many of you are asking, why am I supposed to study astrophysics? I don't care about astrophysics at all. Why am I supposed to do that, regardless of my interests? Well, there are different possible answers. One is because a lot of fundamental physics, and I stress fundamental physics, stems from astrophysics. Dark matter, whatever you like. So the astrophysical aspects of the problem is essential. Or just if you think, okay, I'm not really keen on astrophysics. Okay, you could say the same about weak interactions. Here I wrote quantum mechanics, whatever belongs to fundamental physics. So there's no point to asking why should I start. Well, if you are supposed to take a degree, master degree in physics, there are some topics which you have to know. Astrophysics is one of them, even if that might surprise you a little bit. But for those who are not very keen on astrophysics, there is a good news. The good news is that this is not about astrophysics. And one way to explain that is that the name of the course is Astrophysical Processes. Astrophysical is an adjective. This is not a lecture about grammar, but this is an important point I would like to make. The noun is processes. So to give you a feeling of the way I'm interpreting this course, is that you might look at, we focus on some aspects, of course, just some of them, of the fundamental physics coming from an astrophysical point of view, an astrophysical starting point. Or if you like, we will focus on those aspects of fundamental physics which are particularly important, particularly relevant in an astrophysical context. Okay, so this is just to give you, or another way to put it is just we look at the fundamental physics from an astrophysical vantage point. So astrophysics is just a vantage point, yes, as I showed here. It's not the subject. In many cases, when we will go through fundamental topics, I will stress where this process, where that particular processor is relevant in astrophysics. It doesn't necessarily mean that that's useful also just for astrophysical products, okay? It's just an application in which an application that in an astrophysical context is particularly relevant. Of course, you will understand, you will appreciate this aspect as soon as we go through all these topics. So just having to summarize the main topics we will go through. This is just a bare list. So we will go through, and today we will start from going through some aspects connected with the special relativity that you already know. At least some of them, for sure, you know them. But probably you're not aware of all the consequences. And we will see some of the consequences of special relativity effects that are particularly relevant, that play a special role in astrophysics. So it's kind of astrophysics chooses some of the aspects of special relativity which are particularly relevant to itself. Okay, so then we will move on to radiative transfer. So how radiation is emitted and absorbed by matter, essentially, just to make a very quick summary. We will touch upon some advanced electromagnetism concepts. Of course, in the previous last year, there was a specifically devoted course on advanced electromagnetism. Because of obvious reasons, this is not the equivalent. I cannot touch upon all the aspects on the advanced electromagnetism. I will touch upon some specific aspects which are particularly relevant to astrophysics. And then we will move on to radiative processes. So how matter can produce radiation. Again, in particular, we will focus on some processes, synchrotron radiation, Bremsstrahlung radiation, which are very general topics. but in astrophysics they have a special place. And then, of course, we will move on to dynamics of astrophysical fluids and shock waves. As far as I know, you are not supposed to know, well, unless you have your own interest in, but the physics of shock waves is also very important in astrophysics and is important in physics, general physics as well. So we will go through the mathematical details, what rules shock waves. And you find shock waves everywhere in physics in the world. Then we will see the effect of electromagnetic waves crossing plasmas. We will see how an electromagnetic wave is affected by crossing a region filled up with plasma. There are some specific, and then we will finish up with the mechanisms that are invoked to explain particle accelerations. We see that in the universe there are a lot of particles which are accelerated to extremely high energies. In some cases, energies which are comparable with the kinetic energy of a macroscopic object. So just imagine a macroscopic object like a tennis ball or whatever, having the same kinetic energy of one elementary particles. So the natural question is, who's out there capable of accelerating these particles to such energy? And so there are some mechanisms that have been thought first by Enrico Fermi, and we will go through that. It's also very important. So unless you have any questions, I keep saying they are always welcome. So here, if you are here, just raise your hand, or if you are remotely connected, just say something. I'm happy to answer, if I can. And so let's begin with the very first topic. So this is just a list of what we will go through, and I'm sure that most of you know essentially most of the topics that you see listed here. Some of them should be already familiar, very familiar to you. In some cases, I think you learned them also with myself in your undergraduate courses, and some of them are known, but you will see. So Lorentz transformation, time dilation and proper time, definition of proper time, length contraction, the idea of the concept of the momentum energy for vectors. So the Doppler effect is something which, as you might guess, in astronomy and astrophysics is particularly relevant, but not just in astrophysics. So we will go through the Doppler effect and we will spend some time on it. The aberration of light, which is connected with that. The concept of redshift, which is also a mean to express distances out in the universe. We will go through that. And then more specific topics. In particular, the last one, as you may see, is devoted to the units that are normally adopted for electromagnetic in the electromagnetism. Here we have two systems. The international system, SI, it's abbreviated as SI, not IS, as English would demand, just because it comes from the French, Système International. So in case you wonder, it's not Italian. It's not because when I wrote it, I was thinking Italian. No, this is just French, which I'm not particularly fond of, but nevertheless. And Gaussian system. Why do I devote some slides to this topic? Because usually when I was a student, I remember that when I first studied electromagnetism in my undergraduate courses, the system was the international system. And then when I moved on to the later courses, I found out that particularly elementary physics, elementary particle physics, people, and in astrophysics as well, people like more the Gaussian system. So it's important to understand exactly the differences, how to move from one to the other. So I guess your situation should be the same, probably basic physics, basic electromagnetisms in Physica 2 you studied with the international system, is that correct? But you should have also encountered the Gaussian system, I guess. Okay. Okay, but anyway, when we'll talk about that, you will let me know exactly. So let's start. Let's begin very, very smoothly, very easily, very relaxed with something that you know very well. So Lorentz transformation is transformation which concern inertial reference frames in relativity. So there are a few important aspects which I'm sure are already familiar to you, but it's worth stressing and making sure that to refresh, your knowledge. So we have two systems, in particular, one which is moving with respect to the other. So the black one is what we consider as the fixed system, and the CN one, the one with the cyan colored axis, is the moving one. Here I consider a boost along X, just for simplicity. A boost with the moving system has a velocity v, so it is customary, instead of using the velocity, just to introduce the beta parameter. Beta is just the velocity in units of the speed of light, so v over c. And another quantity which is really, really extremely important is gamma, the Lorentz factor, which is defined 1 over square root of 1 minus beta squared. So you know very well, Lorentz transformation allow you to express, in this case, the space-time vector from one reference frame to the other. Here I put both on the left the Lorentz transformation and its inverse transformation, which can easily be recovered just by changing the sign of beta, of course. And okay, this is a boost along the x-axis. And remember that in relativity, the building block, let me say, are events. So an event is something which takes place in a place. No, takes place in a place doesn't sound really good. That occurs in a place at a given time. So it's just 3 spatial coordinates plus the temporal one. And one of the most important invariant quantities in this case is the delta S squared. So this is an invariant quantity which is related to the metrics adopted in relativity. We will be speaking just about special relativity, so no general relativity. So the space-time I will be always referring to is the Minkowski or flat space-time. Okay. So this quantity is invariant. So it's a Lorentz invariant. So it doesn't change. The value is the same whether you calculate it in one reference frame or in the other one. So the interval between two events, in this case, okay? So I'm not spending too much time on it because this is something that I'm expecting this is just working as a reminder to your knowledge, okay? I'm just refreshing what you already know. But in any case, feel free to ask whenever I say something that you are not very convinced about. Another important factor to take into account is the so-called time dilation, which means, well, let's consider two events taking place in the same point in space in the moving frame. Okay. So I measure, for example, a time. Let's suppose I'm moving. So I'm moving together with the moving system, and the two events I'm considering are, for example, 2 times in which I look at my watch. So I'm moving, I look at my watch once, event 1, and then I look at my watch later on, event 2. So in this case, the two events occur in the same place in the moving frame. The moving frame is my frame. I'm looking at my watch, and my watch is always in the same place for me. So the question is, I will calculate a given time interval between these two events. But the same time interval between the same two events can be worked out also in the fixed frame. So what is the relation between these two time intervals? So between the time interval between the two very same events, but measured into different reference frame. Well, you can work it out with the Lorentz transformation. So in particular, okay, as you see the mouse, here I just took the temporal part of the of the Lorentz transformation, and in the inverse, the prime quantities are the quantities referring to the moving reference frame, okay? So, in this case, T1 prime, T2 prime are the event times of the two events as measured in the moving frame, and T1, T2 in the fixed frame. So, having said that the two events occur in the same place in the moving frame, this means that the two x coordinates are the same, primed. Mind that, primed, because I'm describing these events in the prime system, so in the moving system. So being these two quantities equal, you immediately see that delta t, which is T2 minus T1, I called it just delta t, is gamma times delta t prime. Delta t prime is T2 prime minus T1 prime. Given that delta t prime is a time interval referring to two events happening in the same place, this is also called proper time. And usually in special relativity, in relativity, proper time is denoted with tau. So delta t prime is just delta tau. It's a convention. Okay, so you immediately see that, and this is something that you know very well, something which departs from Newtonian physics. Newton would say, okay, if you take the same couple of events, the same pair of events, and you work out the time interval between these two events, doesn't change when moving from one reference frame to another. Relativity says, no, that's no way. It's no more the case. There's a factor of gamma, Lorentz factor. And in particular, you see that the proper time interval, when is measured, well, when you measure the same interval in the frame in which the two events are not occurring in the same place, the time interval is expanded, is increased by a factor of gamma. And the typical example that is doing here to illustrate, to make the point of the meaning of the proper time, is just consider a particle which is created at some point and then it decays. You might consider the two events, the creation of the particle and the annihilation, and the particle just disappears. Of course, in the moving frame is the co-moving frame, the frame which is moving together with the particle. Of course, the two events and this moving frame do occur in the same place, obviously. So in that case, delta tau is just the lifetime of the particle, measured in its own reference frame. But the time you measure, the lifetime that you measure in the lab frame, is increased by a factor of gamma. So whenever you consider relativistic particles or ultra-relativistic particle, relativistic means that gamma becomes significantly larger than 1. Well, gamma equal to 1 means that the particle is still, doesn't move at all, if you think of the definition of gamma. When gamma starts increasing significantly for just a few, for example, gamma 2, gamma 3, 4, well, that's a relativistic particle. When gamma can be 100, 1,000, in that case, you can speak of an ultra-relativistic motion. And in that case, you see that the lifetime that you measure in the lab frame can be several times, orders of magnitude longer than the lifetime. And this explains, for example, why we see the muons created up in the atmosphere. So there's a lot of also spectacular phenomena that are explained by this. So what I would like to remember this is the meaning, definition, and the meaning of proper time. The proper time is a time interval between two events in an interval of a proper time interval. You can, in general, define a proper time as the time measured in the comoving frame. So you can generalize, and that's the meaning of the integral that you see on the bottom right of the slide. So you integrate between T1 and T2, 1 over gamma, dt over gamma, and you define a generic proper time interval. regardless actually of the kind of motion of the particle. So you can generalize that. So if you like, if you often look at your watch, for example, now it should be, we are approaching lunchtime, so probably you are hungry, so you keep watching, even if when you move and you keep watching, all the time you watch, you watch your watch, you look at your watch, that's something occurring in the same place in your moving frame. So the time intervals are just proper time, proper to you, your own proper time. So every observer, every particle, everything which is moving has its own proper time. His, her, his, its, whatever. The other quite famous effect is so-called length contraction. So if you have an object, consider something which has a particular specific length, which is moving, so again, you can wonder what's the length measured in the two reference frames. So in the co-moving frame, so the frame in which the object doesn't move, is still, and the other one. So in this case, let's consider an object which is at rest in the CN axis reference frame. So is at rest in the moving frame. So again, measuring the length of something, it means measuring the two endpoints at the same time, if the object is moving. If the object doesn't move, well, you can measure the location of one point, one boundary, and the location of the other boundary, even at different times. If it doesn't move, there's no problem. But if it does move, you have to make sure that you measure the position of both boundaries at the same time. Otherwise, you get the measure would be just fooled. Okay. So it means that the two events have to be necessarily simultaneous in the fixed frame, the frame in which the object is moving. And so here, again, just taken from Lorentz transformation, you want to measure the position of the two boundaries, so x1, x2. Well, here is just x prime 1, x2 prime, if you think of the comoving frame. So you have to consider two events that are simultaneous in the fixed frame, which means t1 has to be equal to t2, not t prime. Mind that. In the comoving frame, you don't care about what time. Even if you measure, as I said, the two boundaries at different time in the comoving frame, that's not an issue because the object is still doesn't move. And so you see that if you call delta x prime as x2 prime minus x1 prime and delta x as x2 minus x1, you see that there's again a factor of gamma. In this case, when moving from the comoving frame to the lamp frame to the fixed frame, gamma works in the opposite way as for times. In this case, is contracted. So if I call, as I did here, L0, the rest length, so the length of the object measured when it's at rest, when it doesn't move, and we call it L0, which is exactly the length that is measured by the moving observer, and you compare with the length of the same object as measured in the lap frame, L, the observer, so in the lap frame, you will see the object as it is shortened by a factor of gamma. So you again, if you think of all the possible values of the Lorentz factor, you immediately realize that for relativistic or ultra-relativistic objects, the length contraction can be quite significant. And here, just let me make the first comment relevant to astrophysics. Unlike elementary particle physics, in which if you want to have an object which is relativistic or ultra-relativistic, you necessarily end up with an elementary particle. In our everyday world, you cannot think of a macroscopic object moving with a speed close to c. In astrophysics, this is indeed the case. In astrophysics, as I will mention during this course, there are amounts of mass which can be comparable to the mass of the sun, which are seen to move at ultra-relativistic speed, even with a Lorentz factor of several hundred or 1,000. So the special relativity effects are huge in that case, even for macroscopic objects. So this is kind of peculiarity in astrophysics. At least as long as humans will not be able to accelerate macroscopic objects to that speed, which is not going to happen soon, I guess. So another quantity that it's important to remind is the so-called full vector. You know that living in the space-time is just a four-dimensional space with its own metric that I will mention. So there are objects which live in the space, so the space-time. So you see that the position of something and the time of events are not separate entities, but work together. Say they transform together when moving from one frame to the other frame. So the same argument works for the momentum energy for a vector. You should already know that linear momentum is not something unrelated to energy. They both belong to the same physical entity, which is the so-called momentum energy for a vector. So whenever you want to calculate, for example, you know an object or an elementary particle, whatever you like to think of, and you know its momentum and its energy in one reference frame, if you want to calculate the momentum and energy of the same object as seen in another different frame, you have to go through Lorentz transformation, because the two guys, linear momentum and energy, belong to the same object. So they transform in a connected way. They are related. Again, this is another very important point, peculiarity of special relativity with respect to Newtonian physics, okay? And well, here, of course, the momentum is a vector, so it has three scalar components, x, y, z, and energy is a scalar, and so you have four scalar. And here, just to make sure that you have a homogeneous four vector, homogeneous, so the same unit of measure. Energy is not homogeneous with momentum, so I just put it here, energy over c, and so that to make sure that you have a homogeneous quantity. Okay, so again, you see that the two coordinates that get mixed up are, in this case, the x component along with the time or energy in this case. This is just because I'm considering just a boost along x. If you consider a more generic boost, also y and z components just get mixed up, okay? So just for simplicity. So using a more a notation which is specific to relativity is the so-called Einstein Summation Convention. So when you want to express the invariant quantity, remember, so the so-called, the equivalent of the interval square that I mentioned for the space-time vector, here is just what is denoted by p mu, with this strange convention that we'll mention later on. This is the Einstein convention is supposed to be a sum. So mu is an index which runs from 0. 0 is the temporal or energy component, and 1, 2, 3 is just the spatial component, or x, y, z. So the Einstein convention means, okay, when you see something like that with the same index repeated twice, it means that there is a summation. This is a sum, with mu running from 0 to 3. Okay? And here I just explicitly wrote it as P0 minus the spatial components. In some cases, in some textbooks, you will see the opposite convention. Instead of using the minus sign for the spatial and the plus sign for the temporal, the opposite convention is used. Okay, that's just a matter of convention. Just make sure you are consistent with the choice you make. Okay. So you see that this is an invariant quantity. So this quantity, E squared over E over C squared minus P squared, is invariant, which means no matter in which reference frame you calculate this, this will always give you the same value. And this is very useful for many reasons. And okay, this is the so-called metric tensor, which is the metric tensor of the flat space-time. As I tell you, as I already told you, I'm not considering reference frame which are not inertial. So that's the domain in which special relativity. Otherwise, you have to move to general relativity, which is I'm not doing. And there's also a devoted course on general relativity, which is the one by Professor Pagano, in case you want. Told you. So these are the and why this? Well, you work out. You see that if you use this multiplication of this matrix of the metric tensor by the vector p0, p1, 2, 3, you end up with the very same mathematical expression. So in being invariant means that no matter in which reference frame you calculate it, you get the same result, which means that if p prime mu are just the 4 coordinates of the momentum energy of the same object, the same particle expressed in the moving frame, you get the same. Of course, among all the possible reference frames, there's one special, which is the reference frame, the so-called co-moving frame, the frame in which the object doesn't move. So if you work out the same quantity in that specific frame, of course, the momentum is 0 because the particle isn't moving at all. So in that case, the energy is just the rest energy of the particle, mc squared. And so this the fact that the four magnitude, let me call p mu. You can call it also the 4 magnitude squared of the 4 vector, 4 to remind ourselves that it's in the space-time sense. So you end up with also a very important formula which expresses the energy, the total energy of a given particle as a function of the rest mass and momentum, just from the invariance of this quantity. You see, very easy. So this is a way of exploiting this property, the fact that you have this invariant quantity, to derive a very handy formula. Another way to express the 4 momentum energy, p mu, is a function of the so-called 4 velocity, which here I denoted with capital U. So capital U is a 4 vector and is defined as dx mu over ds, where ds is the interval, the invariant. So ds is an invariant quantity, it's a Lorentz invariant, which is also c d tau. ds is c d tau, yes, because again, if you measure ds in the co-moving frame, the only quantity which is not zero, which is non-zero, is the time interval. So by definition, the 4 velocity is dx over ds, and you see you have a 4 vector dx mu. Well, it's an infinitesimal vector. It's a very small vector, but it's still a 4 vector because the x mu is a 4 vector. So a 4 vector over a scalar, an invariant, Lorentz invariant scalar, ds. ds is an invariant, is a Lorentz invariant. So 4 vector over Lorentz invariant is a 4 vector as well. So the u, the 4 velocity u is also a 4 vector. And if you work it out, you see that you can also express as a gamma, the tempo. I usually, when I write the component of a 4 vector, the first I is meant to be the temporal or energy one, okay? And then The following three ones are the spatial or the momentum in this case. So gamma and beta vector, which is just the velocity vector in units of the speed of light, times gamma. So this is also very useful. If you remember that this object is a 4 vector, your life can be much easier in the following calculations. And so you see that the momentum energy can also be expressed as a function of the 4 velocity as mc u mu, or m gamma. This is just the way depending on the way you put it. Mind that in my definition, well, it's not mine, but the definition I adopted here of 4 velocity is an adimensional quantity. You see, if you look gamma is a number, gamma beta is adimensional. In some other textbooks, in many textbooks, you might see that the 4 velocity has the units of a velocity, which is also reasonable to some extent. So in that case, the definition is dx mu over d tau. So the only difference is just c, speed of light. So in this case, I define the 4 velocity as just the 4 vector related to the velocity in units of c. In other textbooks, you might find just with times c. So it's a velocity. It depends. Just make sure you're not confused by that. So again, because of that, just starting from that, you immediately see that you can express in a generic reference frame in which the object has a velocity v and so a Lorentz factor gamma. You can express both the linear momentum, so p vector, as mv, which is the Newtonian definition, times gamma. So there's an extra factor of gamma with respect to the Newtonian physics, okay? The same works for the energy, with an important difference with respect to the Newtonian case. In this case, the energy, when the particle isn't moving at all, gamma is 1. So you see that this is not the kinetic energy. This is the total energy. So when gamma is 1, when the particle doesn't move, the total energy is the rest energy, mc squared. You immediately also recover the Newtonian equivalents of these expressions, particularly when the particle is not, when the particle or the object, whatever you consider, is not relativistic. It means that gamma is very close to 1. If you think of the definition of gamma, you immediately notice that gamma cannot be lower than 1. It's 1 over square root of 1 minus beta squared. So gamma cannot be lower than 1. The lowest value possible for gamma is just 1, when the particle is still doesn't move. As soon as it moves, gamma starts increasing. Okay, but as long as the particle isn't moving at relativistic speed, gamma is very close to 1. Little bit larger than 1, but very close to it. So you see that the momentum is essentially mv. So you recover the Newtonian formula, which makes sense. Okay, you remember that you constantly have to be able to recover what you already know from the Newtonian physics in the non-relativistic regime. This is important. So you can define the kinetic energy as the total energy minus the rest energy. And that's indeed the kinetic energy. So that's indeed, if you work out the simple exercises that I used to carry out in my undergraduate course, which is to expand, Taylor expand the Lorentz factor gamma. So when the velocity is small, you can expand gamma. Lorentz, you make a Taylor expansion and you recover the classical formula for the kinetic energy, which is 1 over 2 mv squared. Okay. So, okay, it's already 50 minutes. I will usually have classes of 1 hour and a half or 40, depending. No stop unless you strongly demand it. And particularly now, I'll try not to be too long because of the technical inconvenience and of the time taken by the previous lecture. So let's start. So far you should have said, okay, I think I knew that. Okay, it was a useful refresh, but I essentially knew all of that. If you don't, well, you are gonna encounter several problems, several issues. So I'm too hoping that what I've just said so far is just a reminder of what you were. Okay, I was really familiar. Oh, this kind of classes is really boring. I'm keeping hearing something. Wait a moment. Now you start something which probably departs from, not entirely, but at least in part. So in astrophysics, not only, but here specifically in astrophysics, it's very interesting to figure out exactly what happens when a source of radiation is moving with respect to the observer, for obvious reasons. In particular, it's interesting to compare the frequencies of the frequency of the radiation as it is emitted by the source with the frequency perceived, measured by the observer, and also the direction of the radiation. And here there are two effects which we will be have a look more specifically. The so-called Doppler effect that you know very well. So Doppler effect is something that affects the frequency measured by the observer, the frequency of kind of wave. We know light is a wave, but you can talk about Doppler effect whenever you are interested in measuring waves. And in particular, we know from Newtonian physics that Doppler effect comes into play whenever you have a relative motion between the source and the observer. And also the angles measured between the source direction and the velocities of, with relative velocities between observer and we will see again that another effect comes into play, which is the so-called light aberration, aberration of light. And we will see that in relativity there is something called relativistic beaming, which is particularly interesting. This is an important point. Sometimes some time ago, I used to ask this question: are Doppler effects and relativistic and aberration of light specific, peculiar of special relativity, or are general effects? The answer is general. If you want to talk about Doppler effect or aberration of light, you don't necessarily have to talk about special relativity. Also from classical, sometimes I say classical, I mean non-relativistic, okay? So from classical physics, Newtonian physics, you should already be familiar with Doppler effect. You should already be familiar with aberration of light. What is aberration of light? But why are they particularly relevant in this context in which we are talking about special relativity? Because there are some deviations as soon as the velocities of either source or observer becomes relativistic. In that case, the effect of Doppler effect and aberration of light due to special relativity, so in the context of special relativity, deviate significantly from what we know in the Newtonian physics. So that's why it's worth devoting some time to that. Okay, but from a qualitative point of view, there's nothing new in relativity. We already know that even the classical example of aberration is just even when you walk during a rainy day, you have to you cannot, even if the rain is coming just vertically, you know that when you are moving, you have to change the angle of your umbrella if you want to shield yourself effectively, to screen yourself. So it's something that is nothing. It's not specific to relativity. That's the point I want to make. Okay, so just to define the frame in which we will be reasoning for some time. So in general, you might consider we have to have in mind two reference frames. The one so-called source comoving frame, which is the reference frame in which the source of radiation, we are talking about radiation, not generic waves, so I will be speaking of source of radiation. light. So the source co-moving frame is the frame in which the source is at rest, just like that. So co-moving, moving with who? With the source. And the observer frame. So here S just shows the source, S stands for source. And of course, if you look at the source in the observer frame, you see something moving with a given velocity, which is here denoted with a vector, with a red vector. To make things easier to treat, we will conveniently choose a boost along x-axis, okay? So we will assume that the source is moving parallel to the x-axis, just for simplicity, for the sake of clarity. So what is the Doppler effect? Well, the Doppler effect, as I said, concerns the frequency of photons. In particular, we are interested in exploring the relation between the photon frequency in the co-moving frame, as it was emitted by the source, and the frequency measured of the same photon measured by the observer. Well, relativity offers us a very simple way to calculate it, provided that you remember that the frequency of a photon, of course, is related to its energy by h nu, where h is the Planck constant. So if you remember that, and also the relation between energy and momentum for a photon. If E is the energy of a photon and P is its momentum, E equal PC is the relation between energy and momentum. You can also recover from the previous formula if you remember that the mass of a photon is 0. So the way you like it. So let's just use Lorentz transformation along a boost. So you express the momentum energy of a photon in one reference frame and the momentum energy of the same photon in the other reference frame. So just take Lorentz transformation, just like that. And that's what I did here. Well, not yet, but just starting E equal PC is just the energy of the photon h nu in the observer frame, okay? I remind you, prime quantities refer to co-moving frame, unprimed quantities refer to the lamp or fixed or observer frame. And analogously, E prime is the energy of the photon in the co-moving frame, so P prime C, and I could have called it nu prime. It would be okay, but I want here I called it nu 0. 0 stands for because it refers to the frequency measured in the co-moving frame. So the source is at some point for some kind of process emits one photon, and in the co-moving frame of the source, I call nu 0 the frequency of the photon emitted. So 0 is a special meaning because it's the photon frequency in the co-moving frame of the source. So it's something, if you want, intrinsic to the process that the source is going through to emit a photon. And let's assume that while the source is moving along the x-axis, no assumption is made about the direction of the photon. We make no assumption. So in general, the angle of the momentum with respect to the x will be a generic theta. Of course, theta is, we call theta the angle of the momentum of the photon, so the direction of the photon in the fixed frame. So we have to call theta prime the same angle with respect to the same direction as measured in the co-moving frame, okay? So the gain is always the same. So here, I didn't bother write the Py, Pz components. I don't care about them. This is just a boost along x-axis. So the only components that get mixed is just energy and linear momentum along the direction of motion, so Px. That's why I didn't bother just writing the other ones. So just use Lorentz transformation, just like that. So you take the x component and the temporal component, in this case the Px and E component, and you just replace that, remembering that relation between energy and momentum, E equal Pc for a photon, as I said. So here I expressed everything just as a function of energy, or E and E prime. So this is just Lorentz transformation, if you work out. Just to be more explicit, E cos theta would be X if you think of the Lorentz transformation in terms of X, Y, Z, T. This is just X, and beta is just V over C, and this is just the equivalent of time here. Lorentz factor gamma is the same, and this would be just X prime, if you think of that. This would be just T prime, CT prime. This would be CT, and this is just X. E cos theta is just X. I don't know if I'm confusing you or I'm just trying to illustrate that this is just Lorentz transformation. I'm just applying Lorentz transformation straight away. If you understood these four relations, that's just a matter of applying Lorentz transformation. And this is particularly interesting if you look at these couple of equations. Why? Because you have two formulae connecting energy and angles of the same photon as measured in the co-moving frame and in the lap frame. In particular, if you take the second equation, you collect E and you divide, you immediately see that the ratio between E and E prime is this guy, 1 over gamma times 1 minus beta cos theta. But if you remember, energy of a photon is proportional to its frequency. So the ratio between the two energies is also the ratio between the two frequencies. So energy as measured in the lap frame over energy in the co-moving frame is exactly the same ratio as the observed, the measured frequency over the frequency of the same photon in the source co-moving frame. You see that I call this ratio with delta. This is, as you may read from the title, this is called Doppler factor. So the Doppler factor, by definition, is the ratio between the frequency, the observed frequency, and the frequency in the co-moving frame of the source. And you see that here, we will explore in a moment more in detail the meaning of that quantity. But this is worth being learned by heart. You know what by heart means in Italian? By heart, not because you are particularly loving this formula. A memoria, by heart, for those who know, who doesn't know. So this is worth to be learned by heart. So please, learn it by heart. This is one of the most important. It doesn't take too much. If you like, you can also get something else from this equation. If you work out the ratio of the, in this case, the first one over the second one, you immediately see that E prime gets away, cancels out. You are left with cos theta prime. So you have cos theta just as a function of cos theta prime is a function of cos theta and beta. So this formula tells you the direction of the photon as measured in the black frame as a function of, sorry, the other way, the direction of the photon in the co-moving frame of the source as a function of. You can get also the inverse formula. You can invert it just as an algebra exercise, or just thinking more physically. You invert things by changing the sign of beta. You move, when you want to get back in a Lorentz transformation, you get the same result provided that you change the sign of beta, which is equivalent to say to take minus v instead of v. And you will see that in that case, in the second formula I reported here, is indeed the direction of the photon as seen by the observer as a function of the direction of the photon as emitted in the source frame. This also will be particularly relevant. I'll get back to it. But let's focus first on the Doppler factor. So the important point is just to remember the meaning, because if you wanted to apply a formula, you have to know exactly the meaning of everything which shows up in that formula. So here you have, well, you have beta. What is beta? Well, beta is related to the velocity of whom? of the source. So you have a source of radiation, which is moving. So that source has its own beta, its own gamma. So you immediately know beta and gamma. And what is theta? Well, the meaning of theta is shown in this cartoon here. So theta is the angle between the velocity of the source and the ray of light, which is coming to you. Okay? So when the source is moving exactly towards you, theta is 0. One might wonder, okay, I'm not stupid, you don't need to say this. No, but because there are some confusion. In some case, you can take this or pi minus theta. So that's why I'm just pointing out very clearly, because I want to. So if you look at this very simple cartoon and you fix it in your mind, you will not get, you're not going to get into troubles whenever you have to apply this. It's very easy to remember. So theta is just the angle between the direction you look at the source and the direction of the motion of the source. Okay? And it's also called Doppler boosting. Why this? Well, because if the source, you will see, but typically when the source is kind of approaching towards you, you already know from a qualitative point of view, also from Newtonian physics, that whenever a source of radiation is approaching to you, the frequency increases. So the perceived, the measured frequency of the observer is higher than the frequency of the photon in the comoving frame of the source. So the Doppler factor is larger than 1. That's why people talk about Doppler boosting. Doppler increases the photon's frequency. By which amount? By the Doppler factor. So you see that the Doppler factor not only does it depend on the speed of the source, but also on the direction. Again, nothing new with respect to with the Newtonian physics. It's something you already know. Okay, this is just to remind you that theta in this formula is in the observer frame and has that meaning. By now you might wonder, so what's the relation between the Doppler effect in special relativity and what I used to, you might remember from your previous studies, oh, I put a great effort in learning and remembering everything about the Doppler effect, and now what's the relation, what's the connection with this, with the analogous effect in special relativity? Well, you should recover somehow what you already know in the non-relativistic regime. So let's have a look what happens in that case. Non-relativistic means that beta is much smaller than 1. Beta is just V over C. So V much smaller than C means beta much smaller than 1, and gamma close to 1. So in that case, if you take that formula, you see that you recover, so beta is just 1, or better, V over C, not 1, sorry, it's gamma, which is 1. So gamma just 1. V over C, you multiply both the numerator and the denominator by C, you get this, easy. And now if you remember the Doppler effect, as you learned in your undergraduate studies, you should immediately see something very familiar to you. So this is indeed the formula that you get when the observer doesn't move. You have a moving source with a velocity v, with an angle theta, and where the speed of the waves, in this case is light, is indeed c. So this is something that should already be familiar to you. But you see, you can also play the same game now in the comoving source. In the comoving source, who's still, who's moving? Well, in the comoving source, of course, by definition, the source is still. And as a consequence, the observer is moving. So let's take the same formula from the previous slide, which expresses energy and theta, but having now taken the one with theta prime, which is the angle in the source moving frame, which is what we care now of. In that case, if you remember delta, well, delta is written over there, so you immediately see that you can also find another formula for delta, now as a function of theta prime instead of theta. And you see this guy. Again, I remind you, delta is by definition E over E prime. So if you start from here, you see that E over E prime is just gamma times 1 plus beta cos theta prime. While if you express delta as a function of theta instead of theta prime, you see again here, the same guy is at the denominator, except for the, so there are some differences. But that's the same, it's still delta is the same quantity, expressed in two different ways. Why is this so relevant? Because again, if you play the game just of the non-relativistic regime, gamma is 1. You multiply numerator and denominator by C, you get this. You see this? This should remind you the formula for the case in which the source is stationary, which projects to the line between observer and source is theta prime. So approaching observer is a stationary source. So you recover both. And of course, the special meaning is that when we're talking about the propagation of light, there is no reference frame in which the medium is at rest, because there's no medium. So that's why you recover both. You can consider the problem just in the observer frame, so in a frame in which the observer is still stationary and the source is moving, or the other way around. You consider the problem in the source frame, and so the angle is theta prime in this case. This is beautiful. I think it's worth. So the formula I wrote here on the bottom is just to highlight what I just told you. Delta, so the Doppler factor can be expressed and has two different expressions, depending on whether you want to express as a function of the angle in the comoving frame or in the lap frame. Usually, as a matter of fact, on a practical basis, in many contexts, is more useful this one, where you have theta. It's just a matter of convenience, because in most of cases, you know the angle between the observer and the source in the observer frame. But you have to be aware that there is a perfect symmetry between the two. You can consider, sometimes in some problems, it's more convenient to consider theta prime. Maybe because you know theta prime and you don't theta, so it depends. So the important is to understand it. Then you can make the use you want. Of course, there's no need to learn by heart both. Just learn by heart the first one. The other, you can be derived at any time. I proved you the formula, the Doppler effect formula, just starting applying Lorentz transformation. But there's also another more intuitive way to prove it, which is this one. And I like it because it offers you a different perspective, probably more intuitive. It should allow you to appreciate, to grasp more in detail, deeper, the meaning of all this. So let's suppose there's a source which is moving according to the black arrow. So at the beginning, the source is in A, okay? And when it is in A, it emits a photon, which we will call photon number 1, photon 1. So photon 1 just travels along the kind of gold arrow, gold, orange, I don't know, no gold, orange, whatever. So at time 1, the source is in A and it emits photon 1. So photon 1 is traveling towards the observer, okay? In the meantime, the source is moving. It's moving with a velocity v. So velocity v means beta c is the same. After some interval, delta t e, where delta TE is the time interval as measured in the lab frame. Okay? The source has traveled to C. And when it is in C, it emits a second photon, which we call photon 2. So, in photon 2 begins its travel towards the observer from C after some time. So you wonder, what's the time interval, the time interval of the arrival of photon 1 between photon 1 and photon 2? So you are the observer. At some point you see photon 1 arriving. After some time you see photon 2 arriving. So you wonder, what's the time interval between the two arrival times? Before calculating that, you have to realize that when photon 2 is emitted from C, in the meantime, photon 1 has traveled. And let's suppose has traveled out to B. So when photon 2 is emitted at C, photon 1 is already in B. So the difference in light travel times, so-called light travel times, so the time it takes for light to travel a given path. It's just the light travel time if you think of the dashed line here. Because when photon 2 begins its journey, photon 1 is already in B. So let's work it out. So delta TA, where A stands for arrival time, okay, is just AB, it's just the length of the dashed line over C, just like that. So the length of BC is just AB minus AC projected, so AC cos theta. So the numerator here, AB minus AC cos theta, is just the length of this dashed line. But given that this is traveled by something which is traveling at the speed of light, if you want to turn into an arrival time, you have to divide by C, just like that. And that should be, I hope it's clear. If it's not, please let me know. So replacing AB is the path traveled by photon 1 in the time interval delta TE. So it's just C delta TE. But AC is the path traveled by the source. So V or beta C times delta TE. Cos theta is the same. So you can collect delta TE and you are left with 1 minus beta cos theta. And now mind that delta TE is not the time interval between the emission of the two photons in the source frame. This is in the lab frame. We want to know the time interval between the emission of the two photons in the source comoving frame. That's what matters to us. And here you necessarily have to go through a Lorentz transformation from the lab to the comoving source. But you see, the source, the emission of the two photons, is something which happens in the same place in the comoving frame of the source. See, so it's a proper time interval. So when you're moving from a proper time interval to a lab time interval, you have the time dilation, so you gain a factor of gamma. So delta TE is gamma delta TE prime, where delta TE prime, I could have called it also delta tau if you want. Delta TE prime is a proper time interval. That's exactly the time between the emission of the two photons. So this gamma, this factor of gamma, does come from Lorentz transformation. So, in the end, we are interested in reasoning in terms of frequencies rather than time intervals. But if you think carefully, let's suppose that these two photons are just the two next maximums of a wave. So the time interval is just 1 over the time interval is just the frequency. Just like that. Okay. If you think of a source emitting a sequence of photons, if you consider just two next photons, well, 1 over delta T is just the frequency. just like that. So delta t, 1 over delta t arrival is the time interval as measured by the observer. So 1 over is the frequency measured by the observer. So I call nu, following the same notation I adopted in the previous slides, where I call nu the measured frequency. So here I do the same. And I call nu 0, following the same notation, what? The frequency in the co-moving source frame. Having said that delta t e prime is indeed the interval between the two emissions of the two photons in the co-moving source frame, so 1 over delta t e prime is nu 0. So is the photon frequency as measured in the co-moving frame of the source. And so you see that if you replace delta TA and delta TE prime with the corresponding frequencies, you see that the time intervals are related to one another with what you recognize as the Lorentz factor, the Doppler factor, sorry. You remember Doppler factor is 1 over gamma times 1 minus beta cos theta. Here you have gamma 1 minus beta cos theta at the numerator, so it's 1 over delta. But given that time intervals and frequencies are reciprocal to one another, so it means that if time intervals scale with a factor of 1 over delta, frequencies scale with a factor of delta. And indeed, that's what you see. So we proved in a, as I said, more intuitive way, I would say, where does the Doppler factor formula comes from. And this is also useful because it immediately allows us to appreciate the dual aspect between frequencies and the intertime intervals. You see, time intervals just scaling in the opposite way, 1 over delta. And this is, to some extent, this is obvious if you think of the meaning of a frequency. Okay. Consequences. Well, let's suppose you have a spherical source whose surface is expanding radially, okay? In astrophysics, there's a lot of examples. For example, the supernova, a star which is exploding, so its outer layers are expanding, sometimes can also be expanding. Not at relativistic speed unless you take some specific object, but there are objects which are expanding. So the surface is expanding with some Lorentz factor gamma. It's expanding radially, okay? But it's a surface which is also emitting radiation. So if you think of a portion of the surface, you have something which is emitting radiation and which is moving with some Lorentz factor and with some velocity. This is interesting. So, because for example, if you want to know, let's suppose that for simplicity, the radiation emitted by this surface, you are focusing on just photons that have a frequency nu 0. In which frame? In the frame in which the surface is moving, so in the co-moving frame of the source. So you wonder, myself as an observer, what kind of frequency am I supposed to measure? The Doppler factor formula tells you. So if you consider, for example, this surface element, and you want to know what frequency we'll measure coming from the source element, well, you have to know, you have to realize that the source element is moving, the velocity of this element is moving with a velocity which forms an angle of theta with respect to the line of sight. And so you have to apply the Lorentz factor. So where here, gamma is the Lorentz factor of the expanding surface, as theta is just this angle. So you see that if you consider different points along the surface, you have different theta angles. So from different points, you will perceive a different Doppler factor, so different frequency. Because the projected velocity towards the line of sight changes. something that I haven't commented yet, but I do want to do is look at the formula of the Doppler factor. So essentially, also having in mind what I showed you before when I recovered the non-relativistic regime in the two cases. Essentially, the novelty, the new thing that shows up in relativity with respect to the Newtonian case is this guy, the Lorentz factor, because the other part is essentially the same. The real novelty of special relativity is the presence of the gamma factor. There's no equivalent in Newtonian Doppler effect. That's a real new thing. So you are expected to see great deviations from what you know from Newtonian Doppler effect, particularly when gamma gets much larger than 1. That's where special relativity strongly deviates from Newtonian physics. Indeed, that would be the case. But this is just an example, for example, in which you have a practical example in which the Doppler effect comes into play. So it's interesting to study the value of the Doppler effect as a function of theta. So it is a function of theta. There's no question about that. But let's explore, as a matter of fact, how much is it? But to answer this question, you have to figure out what kind of theta values you consider, because it's a function of theta. It might seem obvious, but it is not, as you will see. So let's consider the most obvious value, theta 0. So the source is pointing towards you. The source is moving exactly along the line of sight towards you. So theta 0, well, is gamma 1. Well, it's just that value. But the interesting value is when you consider an ultra-relativistic motion. So when the source is really strongly relativistic. So when gamma is not just larger than 1, is much larger than 1. What happens? To prove that, remember that if you remember the formula for gamma, you invert it and you derive beta as a function of gamma, which is this one, E is again. But when gamma is much larger than 1, you see that it's a square root of 1 minus something small. So you can Taylor expand it, and you get something more or less like this. This is very useful to remember. And if you don't, well, it's easy to recover, but it's used so many times, so repeatedly, that I inevitably, after many years, I inevitably learned it by heart. You're not supposed to learn by heart. But it's useful to remember this. If you replace this into that, well, here, this is also another formula for the Doppler effect in the case when the source is pointing exactly toward the observer. But if you replace, in the case of gamma much larger than 1, you recover this 2 gamma. There's a factor of 2. It can be easily seen if you replace this one here. 1 minus beta, you see that you get 1 over 2 gamma squared, so 2 gamma at the numerator. So what does this mean? You see, it means that the Doppler factor, when the source is moving towards the observer, the Doppler factor is a factor of 2 gamma, which is very high. But not only very high, we know exactly how high it is. And if you consider not theta 0, but theta close to 0, so a small angle, so the source is not pointing exactly towards you, but slightly off axis, but slightly off, but almost towards you. Okay. Well, in that case, you can Taylor expand not only beta, not only gamma. Well, if you Taylor expand theta, because theta is a small angle, also cos theta, here we have cos theta, so cos theta is 1 minus theta squared over 2, just like that. You see that you recover this formula. But what is interesting is that let's consider a specific angle. When theta is 1 over gamma. Well, if gamma is much larger than 1, 1 over gamma is a small value. So it does apply to this. And in this case, you see when theta is equal to 1 over gamma, you see that the Doppler factor is nearly the Lorentz factor itself. So this figure here is showing exactly, here you have the source, and the magnitude of the arrow is proportional to the Doppler factor. So you have the highest value, which is 2 gamma. I apologize, here the figure used capital gamma. I use small gamma. Here it's meant to be the same quantity, okay? So here you see when theta is 0, you have this case, and the Doppler factor is maximum, and you have 2 gamma. When theta is small, how much small? 1 over gamma. In this case, you see the Doppler shift, so the Doppler factor is just gamma. It's exactly what we covered here. So when moving from 0 to 1 over gamma, the Doppler factor changes from 2 gamma to 2 gamma to 2 gamma. And so we are talking about gamma much larger than 1. So photons whose frequency is significantly larger than the source co-moving frame frequency. Okay? So it's a boosting, it's a real boosting. If you consider the opposite case, so the photon which is emitted in the opposite direction, so theta is just pi, you see that you have the so-called deboosting. So in that case, of course, the photon perceived is much so the observer in that case is, of course, so the source essentially is moving exactly in the opposite direction with respect to the observer. So again, from a qualitative point of view, you shouldn't be surprised. You shouldn't say, "Oh my God, my goodness, I didn't expect it." No, you should have expected. Another effect is the so-called relativistic beaming, or headlight effects, because it reminds of what you see coming out of your car headlights. Let's consider the formula between cos theta and cos theta prime that I derived a few slides ago. Now we wonder. We start in the upper panels. Here you see the process in the source co-moving frame. S prime is the source in which the source is at rest. So these panels up here are the co-moving frame of the source. And here, the lower panels are the observer frame. Let's consider specifically one photon, which in the co-moving frame of the source is emitted towards a direction which is perpendicular with respect to the direction of motion, which is this angle here, up here. The source is moving this way, well, not in this reference frame, of course, in this one, but the direction is that. So the source has emitted in its own frame a photon whose angle is theta prime is 90 degrees, so pi over 2, with respect to the line of motion. So we wonder now, what's the direction measured by the observer of the same frame, of the same photon? Just use that formula, just like that, because it gives you theta as a function of theta prime. Theta prime in this case is 90 degrees, so cos theta just vanishes, and so this is just beta. But cos theta equal beta, if you remember, we are particularly interested in the ultra-relativistic case, when beta, also when gamma is much larger than 1, or significantly larger than 1. But in order to have gamma of several, when I say several means 5, 6, 7, 8. A few is 1, 2, 3, 4. Several is 5, 6. Well, more or less. It's not. There's no strict. Just to give you a feeling of that. So even if you want to have gamma of a factor of several, or even just slightly more than a few, beta has to be very close to 1. So beta very close to 1. When is that? Because cos theta is very close to 1. When theta itself is very close to 0. So you can, again, Taylor expand beta, same formula I showed you before. And given that theta is small, you can Taylor expand theta as well. So comparing the two Taylor expansions, you immediately see that theta is 1 over gamma. What does this mean? The answer is this figure. So you are wondering, what's the direction of that photon, which in the source frame is emitted 90 degrees with respect to the direction of motion? The very same photon will be seen by the observer very close to the direction of motion of the source. How much close? With an angle of 1 over gamma. Since gamma can be higher, relatively high, 1 over gamma is small. And the faster the source, the closer the photon will be seen by the observer close to the direction of motion of the source. That's why headlight effect or beaming effect. It's like a beaming. You are beaming. And you say, why I took 90 degrees? Because if you consider all the photons emitted by the source in this range between 0 and theta, you immediately consider half of the sky of the source. So let's suppose the source is emitting isotropically, so the same amount of photons towards all directions with no preferred direction. Okay. So if you consider, look at the upper panel. If you consider all the photons between theta 0, theta prime 0, and theta prime 90, you consider half of the sky of the source. So it means that at least half of the sky of the source is beamed in this cone. This is a cone whose semi-aperture angle is 1 over gamma. So half of the sky in the comoving frame of the source. So the source is democratic, is emitting photons towards all directions. Half of the sky is just beamed to us, a narrow cone. How much narrow? Well, it depends. The higher the Lorentz factor, the narrower the cone. And this is a peculiarity of relativity. There's nothing like that. Again, why? Because in relativity, the speed of light plays the role of a limiting speed. So whenever you approach this limiting speed, you have the same kind of effect that you would expect, at least in the Newtonian physics, for an infinite velocity. So to have something comparable to that in Newtonian physics, you should travel at infinite speed. So 1 over gamma is very important to remember, is the beaming effect. So when you have a source emitting, even if the source, if you could travel alongside the source, you'd be very happy. Oh, the source is emitting photons in every direction with the same intensity, with the very same phenomenon as seen by the observer. You see just a beam. The source is emitting along its line, along its motion. Okay, I'm almost done. So this is a quite simple sketch of the so-called relativistic aberration. Aberration, what does this mean? It means because something which affects the line, the direction of radiation, the direction of photons. The aberration of light was discovered at the beginning of the 18th century by Bradley, which realized that the apparent position of the stars was changing during 1 year, because the Earth, as a matter of fact, is moving. It's a small effect, but it's not relativistic from a qualitative point of view. You can explain also in Newtonian physics. But here you see, whenever you approach the speed of light, the relativist, you see, in the source frame, which is the same frame as here when the velocity is 0, in that case, the lab frame and the source frame coincide, of course. You see that the rays are all distributed equally, isotropical, I should say. But in the comoving frame, when the source is moving, the faster it's moving, and the more beamed is the radiation. You can play a game on if you like, just working out, making graphs with your own computer. What you need is just this formula, just like that. Here what I did, the exercise I carried out is the following. I took the moving frame of the source, and I showed many rays with a constant step, which is 1.8 degrees step, so a lot of them. And here I just used two colors to mean the hemisphere looking forward, and the hemisphere, the blue one, and the red one is the hemisphere of the source looking backward, forward with respect to the direction of motion of the source. So in the moving frame, of course, the source is still stationary, it doesn't move. So theta prime is the angle describing all these rays. So for each ray, you wonder, what's the direction measured by the observer? Well, use this formula. So you know theta prime, you calculate theta. And you pass from here to here. So you see here, for example, I used beta 0.5, so half the speed of light. And gamma is 1.2, so slightly larger than 1. But yet you see that the blue one, the blue hemisphere, so half of the sky, is approaching 1 over gamma. You can increase beta and increase consequently gamma. In this case, beta is just 0.9, so it gets closer to the speed of light, and the Lorentz factor is 2.3. You see how the effect of beaming increases correspondingly. And here is, for example, when beta is 0.99, gamma is a little more than 7, you see this effect is extreme. You see, not only you have this, but you see that also backward, there are left fewer and fewer photons. So essentially, what the source is emitting that way in its own reference frame, in the observer frame, almost all the photons are emitted forward. How much? By that, you see. So 1 over gamma, you see the meaning of 1 over gamma. 1 over gamma is telling you, oh, half of the sky is there. It's just there in this tiny narrow cone. But also the other part here, these you see, you still have a lot of photons here, which belongs to the other hemisphere. So a lot of radiation is just focused on that, and very little is left here. So the photons are deboosted. Remember, the deboosted are those who are emitted in the observer frame backward. Very few. Most of the photons are boosted. So the effect of having a source of radiation moving at relativistic, ultra-relativistic speed is huge. Not only the Doppler factor tells you the increase of the frequency, but here the aberration, the relativistic aberration, and what is called the beaming, relativistic beaming, is how radiation is distributed in the two reference frames. So here you have the headlight or relativistic beaming effect. So a radiation, a particle, we will consider a particle emitting radiation. In their own reference frame, these particles are emitting isotropic, not exactly isotropical for the cases we will see, but kind of. But this kind of isotropic emission in the moving frame of the particle will be extremely beamed in the observer, in the lab frame, just because the particle is moving at relativistic speed. So the beaming, the relativistic beaming, or relativistic aberration is the same. It's very important. And just last thing I want to say is one of the effects of this is, again, if you consider the previously considered expanding surface with the Lorentz factor gamma, given that all these elements are moving with the Lorentz factor gamma, even if in their own reference frame they are emitting radiation isotropically, you will not see all of them. For example, you will see very well these elements in the red bar here, because the line of sight lies within the beaming cone of the. But if you take this element here, this element here has a velocity which is directed this way. So if you work out the beaming cone, the relativistic beaming cone, you get something like this. So most of the radiation emitted by this element of surface will be in this cone, but this cone doesn't include the line of sight. So you're not going to see that. So the effect from a surface which is expanding ultra-relativistic, it means that you are not going to receive radiation from all the elements of the surface. Like, for example, you see the entire surface of the sun, because the sun doesn't, well, it's expanding sometimes, but not at relativistic speed. So you see all the surface. If the sun at some point would expand radially at relativistic speed, you would see just a spot. You are not going to get radiation from the elements for which the relativistic beaming is too far away from your line of sight. So this is one of the notable effects. I'm starting with, my research deals with these objects which are expanding with a Lorentz factor of 1,000 up to 1,000. So this effect is crucial, isn't it? Okay, I'll stop here, and it's already time to stop. So I apologize for the time, but this is a kind of one-of-a-kind lecture today. So I'll be more timely on Wednesday, 11. Okay. I will grant you the 15 minutes pause from the end of the previous lecture. So please drop me your email address, and I'll make sure that I'm going to share this one, and I'll make sure to share in advance, right before, so that you already have it. And questions? Okay, so see you on Wednesday.
Thank you. Goodbye.
Bye.